Hi everyone, welcome to GemChem. Now today's video is on molecular orbital part 2 video, and here we are going to deal with expression of energy associated with bonding and antibonding molecular orbital and their pictorial representation of radial wave functions, also formation of He2 gaseous and criteria for LCAO to form MO. Now before starting, already one video is uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first we will deal with expression for energy associated with bonding and antibonding molecular orbitals. So we have expression of EB as equals to integration of xi b H, that is Hamiltonian operator, xi b d tau. Xi b stands for bonding wave function, right? Divided by xi b square d tau. Now since the wave functions are normalized, so we can write it integration xi b H xi b d tau. Now if we try to write down the next portion of EB, then we can write it as EB equals to integration 1 by root over 2 plus 2s in bracket xi a plus xi b. Then we have Hamiltonian operator, again 1 by root over 2 plus 2s, xi a and plus xi b, and we have d tau. Once this is done, we can take out 1 by root 2 plus s from both the ends, that is from here as well as here. So we get 1 by 2 plus 2s. In integration we have xi a plus xi b. Then Hamiltonian, then xi a plus xi b and d tau. In next case, what we will do? This expression will be written as like this, that is 1 by 2 plus 2s, and within the bracket you can write integration xi a H xi a d tau plus xi a H xi b d tau plus xi b H xi a d tau, and next integration xi b H xi b d tau. Now what does this mean? For this case, if we consider this one and this one, these are actually Coulomb integral. So see here, C-O-U-L-O-M-B, Coulomb integral, and this Coulomb integral shows that since xi a and xi b are wave functions for 1s and 1 orbital of HA and HB, so we can see that the combination rate between own cells can be seen here. If we consider these two, then these are actually resonance integral. Resonance integral. And this is Coulomb integral is being represented by alpha and resonance integral is denoted by beta. This resonance integral is negative. Now we need to see that this equation, which we can name it as A equation, this A equation can be transformed to a different way. That is, we are substituting these as alpha and these as betas. Let's do that. So EB becomes equal to 1 by 2 plus 2s, and we have 2 alpha plus 2 beta. So if we take 2 common, we get alpha plus beta by 1 plus s. Now if you do the same treatment with anti-bonding molecular orbital, so here in this case you will have, instead of xi b, xi a, and instead of xi a plus xi b, you will have xi a minus xi b. As a result of which your expression will become just the opposite of the bonding molecular orbital, and the expression will be Ea equals 1 by 2 plus 2s, and this will have 2 alpha minus 2 beta, and this will also become minus this part, and we can write it as alpha minus beta and 1 minus s. So usually the value of this resonance integral is negative, as I have already told you. So from the expression of Ea and Eb, it can be said that the magnitude of energy of bonding molecular orbital will always be lesser than that of antibonding molecular orbital. Thus, extent of stabilization of bonding molecular orbital is lesser than the extent of energization of antibonding orbital. Though we write it same, but actually bonding molecular orbital is more or less different in energy than antibonding molecular orbital. So from the formation of hydrogen molecule we can also see, but more specifically from formation of He2 we are going to see how this effect occurs. So let us see the formation of He2 gaseous. Now if we consider the energy level diagram, so how to draw it? We have a energy axis, right? And we need to have 1s, this is our 1s, here also 1s, right? And from here we have a bonding molecular orbital and we have a anti-bonding molecular orbital, which is more energized than the stabilization of bonding molecular orbital. We can name this as helium A and this as helium B. Okay. Now what we do is, first of all we write down the energies. For this one we have energy equals to Eb, and for this one we have energy equals to Ea. Now if we try to write down the xi b here and xi a here, and then followed by filling up of electron. So let us fill up the electrons here. So we have 2 electrons here, 2 electrons here, right? So now filling up starts from bonding molecular orbital. So here will be filling up, here will be filling up. Now this is our He2, right? If we try to calculate the bond order, what will happen? What is bond order? Bond order is number of electrons present in bonding molecular orbital minus number of electrons present in antibonding molecular orbital divided by 2. So this will come as 2 minus 2 divided by 2. So this is 0. This proves that there is no bond formation between two helium. Also from the molecular energy level diagram, it is evident that with respect to energy of atomic orbitals, if you see, the net energization of antibonding molecular orbital, that is this one, is more, right? And it is greater than the net stabilization of bonding molecular orbital. It is for this reason that when two helium atoms are brought close together, they form He2, then they will fly apart, since net energy of hypothetical He2 we have considered will be higher than the summation of energy of two isolated helium atoms. As a result, they are removed from the scope, and this He2 in excited state can be stabilized because we are removing it's 1 electron. So when we are using He2 plus, then what happens? One of the electron is not present, this is removed, so we have bond energy, that is bond order comes to be as 2 minus 1 by 2, which is 0.5. So we can have the existence of He2 plus. Now we will see the pictorial representation of radial wave functions associated with bonding and antibonding molecular orbitals of hydrogen molecules. So if you see here, and if you have seen the atomic structure videos, then you can understand what is radial wave function. So if you want to see, you can watch the playlist. I will give the link in the description box as well as the I button present above this video. So this is our HA and this is our HB. Now these radial wave functions combines together to form the bonding molecular orbital, which looks like this. And this is our Xi B. This can be written as our Xi B, which is equals to 1 by root over 2 plus 2s Xi A plus Xi B. And on further doing this, we can also draw for Xi B square, which will come from the downside of this, merge with this, again from the downside and merge with this. So this is our graph for Xi B square. Now if we go for antibonding molecular orbital, then one will be in phase, one will be out of phase. When these combines, this type of radial wave function is obtained. Now if we try to see the Xi A function, then Xi A is equals to 1 by root over 2 minus 2s Xi A minus Xi B. Okay, and after doing this, if we want to get the radial wave function for Xi A square, then it will come like this. So the both peaks goes in the upside. Remember this. Next we will deal with criteria for LCAO to form MO. Now you have to always remember that the combining atomic orbitals should be of similar symmetry. If they are not of similar symmetry, they cannot combine. And the combining atomic orbitals should be of similar energy for combination. There, the overlap integral which we had talked about between the two combining orbitals should be positive. Why positive? The combined AOs must be able to overlap properly. If it is not positive, then overlap will not be proper. Now we will see few criteria of energy, orbital and symmetry in order to understand the drawing of MO energy level diagram, which we will deal with in the next video. So let us see. EOS. Now this E stands for energy, O stands for orbital and symmetry is for S. Now if we try to draw a diagram of a graph, then we have first lithium, next we have beryllium, next we have boron, carbon, nitrogen, oxygen, fluorine, and now here we have energy. If we consider the overlap between 2s and 2p in case of lithium, it is like this. They are so close to each other. So we have here 2s, we have 2p. Once we progress towards the right side of the periodic table, what happens is that this distance goes on increasing. Here, if we consider for nitrogen, it comes about here, the 2p, and the 2s comes down in this position. Next, further it goes on decreasing, and finally it is so much decreased that it is even down. So here the overlap is very less. This is the gap change which we observe, right? So we have a pattern of gap change present. Energy of 2s and 2p, atomic orbitals for the second row element is being represented. So as we move along from lithium to phosphorus, effective nuclear charge increase, as a result of which the orbital electronegativity, that is the electron density of 2s and 2p, will come closer to the nucleus as nuclear charge is increasing. It is for this reason that the 2s and the 2p will be dragged closer to the nucleus. Thereby their energy is being lowered. Also, since the orbital penetrativity of 2s we know greater than 2p, the extent of decrease in energy of 2s is greater than 2p. It is for this reason that the energy gap between 2s and 2p of O and F are much higher, thereby accounting for the fact that they do not undergo mixing, but others do undergo mixing in their orbital energy. So these are treated special because there is no overlap or combination of mixing between 2s and 2p. But when we will do the orbital molecular energy level diagram for this, then we will see that there will be a mixing. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, comment and subscribe.